morning and welcome to the Embedded Vision Summit. My name is Jeff Beer. I'm founder of the Embedded Vision Alliance, which is the organization running this event, also president of BDTI, small consulting firm. My colleagues and I started the Embedded Vision Alliance about 2.5 years ago because we were and still are very excited about the potential for vision technology to proliferate into all kinds of products and applications. And we thought that we could help make that happen by helping provide practical know-how and resources for engineers like us in industry who may not necessarily be computer vision specialists, may not be experts on every aspect of the technology, but are excited about the possibilities of harnessing the technology to make new, powerful kinds of products. Now, 2 years after starting the Embedded Vision Alliance, it's really exciting to see so many people interested in the same kinds of things we're interested in based on everybody in this room today. So thank you all very much for being here. The Embedded Vision Alliance is a partnership of 33 technology and service provider companies that was formed about 2 years ago to inspire and empower product creators to harness this increasingly accessible and powerful and affordable technology for embedded vision. We do this by providing free, high-quality educational resources like today's event and like our website, which I strongly encourage you to visit. It's embedded-vision.com. If you haven't already done that, please check it out. Please register yourself and sign up for the Embedded Vision Insights newsletter. That comes every other week, and we'll keep you informed about new content on the website, new events run by the Alliance, related events run by other people, and so on. I want to thank all of the 33 member companies of the Alliance whose support and participation has helped make this event possible. And I also want to thank the Alliance staff who've been working their tails off for the last several months to put this event together. The organization's very young. We have a small staff. We don't have a lot of experience running events, so we've been learning on the job, and it's been a lot of work. I really appreciate all the work that everyone has done. And I also want to thank all of our presenters today, all of whom have done a lot of work preparing their presentations, and I think and I hope that you'll find them very insightful, informative, and educational. Speaking of presenters, let me give you a brief tour of the agenda today. I'll be introducing our keynote speaker in a moment, so I'll skip over that for the moment. After the keynote presentation, we'll have a 30-minute break. During this break and all other breaks today, the demos will be open. The demos are in room 230A next door. There are about 25 or 30 of them. They're really cool. Go by and check them out and chat with the technology experts from the member companies of the Embedded Vision Alliance who are here showing the demos and presenting. The demos will be open during the morning coffee break, during the lunch hour, during the afternoon coffee break, and during our evening reception at the end of the day. After the break, you'll come back. This room is going to be divided into two right down the center. During the morning break, this room will be divided into two, and the two technical tracks will be running in parallel. Signs outside the doors will tell you which track is in which room. We'll start with overview presentations in the two tracks. Gary Bradsky, we're very excited, is here from the OpenCV Foundation and Industrial Perception to share with us his latest news about the OpenCV open source library in his overview presentation, and simultaneously in track B, I'll be sharing some of my insights and ideas about what's happening in embedded vision and where it's going. Then we've got our lunch break with demos, and after lunch, we'll start with sessions A1 and B1, again in the two rooms. Session A1 is about sort of implementation aspects, software, accelerator, system design considerations. Session B1 is about applications, some interesting representative applications, including Gary Bradsky will come back and talk to us about some interesting industrial robotics applications, including, if I understood the email correctly, some new results as of last night. Afternoon break, more demos, and then into sessions A2 and B2 in the afternoon. A2 is a continuation of A1, more on implementation considerations. B2 is our session on algorithms, trade-offs among different kinds of algorithms, using different kinds of algorithms for various embedded vision problems. Last sessions of the day, A3 and B3. A3 is about the image sensors and front-end processing associated with image sensors. B3 will start with, actually there's a typo on here, I apologize. B3 will be the what we call rapid fire new product announcements. So we have several new products being introduced here today by some of the member companies, and we want this to be an educational, not primarily a marketing event. So I told them they could each have 5 minutes. It's speed dating. So all the rest of the presentations are intended explicitly to be educational and not promotional in nature. These 5 presentations at 4 o'clock are where our members are introducing some of their new products. I think they're very cool new products that you'll want to hear about. There'll be 5-minute, very quick presentations, and then on the demo, in the demo area, you'll be able to talk to the member companies and get more detail about those products. And there's a session B4 that header got lost here that includes our continuation of our application session focused on automotive safety related applications, arguably the most rapidly maturing embedded vision application right now. And then finally in the evening we'll have our reception, again with the demos from 5:30 to 7:30. That will be in the demo room and in the foyer here and in the overflow seating area out in the lobby beyond the registration desk, the Embedded Vision Summit registration desk where you checked in. Anyway, the logistical details will be reinforced later. You don't have to remember those all now. But I would like to ask you one favor, which is please fill out your evaluation form throughout the day and keep it with you. If you're like me, when it gets to be the end of the day, it may be a little bit difficult to remember what you liked and didn't like first thing in the morning. And that feedback is extremely valuable to us. We scrutinize it, analyze it 7 different ways, and it's really helpful for us to improve our events going forward. Like I said, we're new to this. This is only the 2nd public event held by the Embedded Vision Alliance, and so the feedback is extremely valuable. We appreciate you taking a few minutes as you go throughout the day, fill out the evaluation form, and then you can turn it in at the check-in table on your way out, or just leave it at your chair, and we'll collect them at the end of the day. Finally, I want to thank our sponsors of this event, Xilinx, Analog Devices, Synopsys, Avnet, MathWorks, Qualcomm, Tensilica, Inrevium, which is a brand of Tokyo Electron device, and Vidiantis. These companies, frankly, have paid for this. So thank you very much. We appreciate your making this event possible. Finally, I'm delighted to introduce our keynote speaker, Professor Pieter Abbeel. Pieter received his master's and bachelor's degree in electrical engineering from KU Leuven in Belgium and his Ph.D. from Stanford. He joined the faculty of electrical engineering and computer sciences at UC Berkeley in 2008. As I was preparing this introduction, I found that he has won so many awards that we would have had to extend the schedule today if I were to enumerate them all here today. So I'll just give you the highlights. He's won a Sloan Fellowship, Young Investigator Program Awards from both the Air Force Office of Scientific Research and the Office of Naval Research, the Okawa Foundation Award, the TR-35, and Best Paper Awards at the ICML and ICRA conferences. In addition, his work, for reasons that will become evident to you shortly, has been featured in many popular media outlets, including the BBC, the New York Times, and Wired. His current research focuses on robotics and machine learning, with particular focus on challenges in personal robotics, surgical robotics, and connectomics. When I first invited Professor Abbeel to be our keynote speaker, he told me I had the wrong guy. He said, I'm not really a computer vision guy. I don't really focus my research on computer vision. And your event is about computer vision. And I said, well, yeah, but you may not focus on computer vision, but what you are doing is using computer vision in combination with other technologies like machine learning to really move the needle in terms of what machines are capable of doing autonomously. And that is extremely relevant to our interests and our audience. And for this reason, I think his work is really shining a light that it's will help all of us see some of the possibilities. As our machines, as our systems become more visually intelligent, what can we accomplish with them? So I'm very grateful that Professor Abbeel relented and graciously agreed to be our keynote speaker, even though he thought it wasn't the right guy at first. And I ask that you please join me in welcoming Professor Pieter Abbeel.
Thanks everyone for being here. So I'm going to tell you a little bit about artificial intelligence for robotic surgeons and robotic butlers. Kind of the starting point for me for what I've been working on the last few years is this video over here. So let's take a look at what's going on here. So what we're seeing here is a robot doing the kinds of tasks that many of us would hope robots might be doing for us, doing all kinds of household chores. A bit the Rosie the robot from the 60s, but now in the real world. So this is great. This is a robot doing the things we want robots to do. There's a catch, however. And the catch is that this robot was fully teleoperated, meaning that every single motion of that robot was actually executed by a person sitting in a harness, making all the motions for the robot. So it actually takes more work getting the robot to do this than just doing it on your own. But what it does tell us is that if we can write the correct software to drive the robot, then we actually do have the kinds of robots that could do things for us. And it kind of motivates us to look at the software side of robotics and see what we can make happen there, because if we can make something happen, maybe we can get robots like that. Now, the direction I've been looking at this is that robots are extremely hard to program. Whenever you program a robot for a new task, often you are busy for months, even if you're an expert, to get the robot to do just one new task. And so what I've been interested in is how to make robots learn. And the one particular thing I've been interested in is this thing called apprenticeship learning. And the idea there is that the robot is your apprentice, watches you do things, learns from watching you do things, and then maybe improves a little further on its own. Once you've written the software for a robot to be the apprentice, then all you need to do for the robot to learn something new is to show the robot new tasks, how they're done, instead of reprogramming the robot every single time you have a new task. We're not that far along yet, but I want to tell you about is two stories where we've done this reasonably successfully, one in helicopter flight and one in robotic manipulation. And then I want to, at the end, give you a quick highlight of two other stories of research that I think are quite relevant to what we're looking at here. So, helicopter flight. Why is it a challenging problem? It's a challenging control problem because when you try to fly a helicopter, you have to continuously adjust the controls to just keep it in the air. Helicopters are unstable. If you don't continuously adjust, they'll just drop out of the sky. They're not just unstable, they're also nonlinear, meaning that standard nonlinear control techniques will not work very well for a helicopter. Besides nonlinear, the dynamics is also very complex to model because of the airflow around the helicopter being so difficult to model. Beyond that, there is coupling between the different parts of the helicopter, making the dynamics even more complicated. aside from these complexities, there's the complexity that when you control a helicopter, you actually don't typically have access to the state of the helicopter, because all you get is noisy sensors telling you something about the state of the helicopter, and based on that, you somehow have to control it. Now, despite these challenges, there actually have been quite a few research groups out there that have successfully built autonomous helicopter controllers. And I'm listing a few examples there. And what's interesting about that is that these groups have used a variety of different techniques. Some use inner-outer loop PID control, which could be hand-tuned, or the variables in that control loop could be learned. Some people use H-infinity control, some people use LQR, and so forth. Now, if you look at some of the most advanced results they've gotten, I have a video here by Andrew Ng at Stanford. These are the kind of results you can get with these techniques. This is a helicopter flying upside down, stably. Arguably the most advanced controller of the ones I showed on the previous slide. We said, so Andrew was my PhD advisor. After I did this, I started working on helicopters with him. And we said, well, this is all great, but the helicopter was already upside down before the computer took control. Can't we have the computer flip the helicopter over, do the whole thing on its own? And so we looked at what they did for flying the helicopter upside down. We said, let's use the same techniques and see if we can make it flip over. So let's watch that result. Got the helicopter to flip. This is all autonomous. And then we lost our helicopter. What happened? Well, we were controlling that helicopter autonomously. It was exerting the control inputs too much. The engine died, and there it lost control. It turns out the pilot, safety pilot, actually took control back. The helicopter went behind the trees, engine off, but you can auto-rotate helicopters in principle, not if you're going fast, down that quickly, but at least a little bit. Without seeing the helicopter, he could flip it back right side down and land it on the landing gear. Now, it was a very fast landing that crashed the helicopter, but just to say how human pilots were just still a lot better than these computer pilots at this point. So what's so different about stationary flight versus aggressive flight? Because that's really what we're after here. Hover, inverted hover, or forward flight, those are flight regimes where you are always in the same regime. Whereas if you try to flip, then the airflow around the helicopter will drastically change as you go throughout the maneuver. And that's really the key difference here between what had been done before, namely flying in stationary flight regimes, versus what we're trying to do with our research, which is flying the entire flight envelope, including non-stationary flight regimes. In stationary flight regimes, essentially what you can do is collect data, build a model for your helicopter in that particular flight regime that you care about. And that's possible now because it's just one flight regime, so you don't need too much data to do that. You have a simulator at that point, and then based on that simulator, you can then design a controller using standard linear control techniques or H-infinity or whatever is the standard way of designing a controller to stay around a specific point. For aggressive flight, it's a little different. First thing you have to do is you have to decide what it is that your helicopter should be doing. It's not just staying in a particular state. It's going to have to do, let's say, flips. What does that mean? To apply control techniques, you need to somehow have a trajectory. You need to know at what position and orientation you want your helicopter to be over time. You can't just say flip. You have to say position orientation at each time. Try to stay as close as possible. But if you pick something that is not flyable by your helicopter, then you're trying to follow a target that's just impossible, and what happens is what you saw. We picked a target that wasn't right for the helicopter. You end up exerting the controls too much to stay on track, and it fails. Second thing you need is a good dynamics model. So many modern control techniques, the way they work is you have a target, you have a dynamics model, and then what you do is as you control your system, you will simulate maybe looking 2 or 5 or 10 seconds ahead, and over that window, you will plan for the optimal sequence of controls to stay on target. You will then execute the first set of controls in that sequence, and then you will replan maybe a tenth of a second later. That's called model predictive control, and that's what most people do these days. But it requires a good model to be able to do that. All right, so we looked at the literature and looked at, was there anybody out there who could fly in non-stationary flight regimes? And it turns out there was a group out there, namely Eric Frohn's group at MIT. They had done 3 maneuvers: split S, snap axial roll, and stall turn. And the key insight from reading their papers was that they recorded human pilot trajectories, carefully analyzed them, and then designed controllers that had the same behavior as the human pilot. This took quite a bit of time. This took essentially a Ph.D. thesis of work to do 3 maneuvers, an MIT Ph.D. thesis, so a good Ph.D. thesis. We said, if we want to fly the entire flight envelope of the helicopter, we need to do something that will automate that process, such that whenever a pilot flies, maybe we can automatically learn what the pattern is that they follow, and from that then fly autonomously. And if we can do that, then we can just let a pilot fly a lot of maneuvers in sequence, learn to fly all of them maybe in one day. So the first thing we need to learn from the pilot's demonstrations is the target trajectory. It's difficult to specify it by hand. Why? Because the dynamics of the helicopter is so complicated. It's really hard to specify a sequence of positions and orientations that are actually flyable. So we said, let's collect pilot data, not just one demonstration of a trajectory, because one demonstration will be noisy. The pilot will not be doing exactly what they intend to be doing. We want a cleaned up version, so we want to get multiple demonstrations and somehow extract the clean version out of these multiple demonstrations. So here's what this looks like. We go out with our pilot. He'll fly our remotely controlled helicopter. Then while he's flying, we track the helicopter. And here's a replay of 6 demonstrations by our pilot of flying an air show. Now, if you look at this carefully, you'll see these 6 helicopter demonstrations. All 6 of them go through the same sequence of maneuvers, not with the same timing, not the same location, not exactly the same orientation, but the same pattern. So right now, they were all in a double loop. If you were to just average these, you will get out garbage. In general, for nonlinear systems, just averaging their trajectories will not give you anything that's reasonable to try to execute with that system. But you can see that there's a pattern there that, as people, we can extract, and we might be able to imagine or dream up what the intent was that the pilot had, and hopefully we can come up with an algorithm that extracts that for us. So let's take a look at how that might work. What we'll use is something called a hidden Markov model. And the way that's set up is that you have a sequence of states. Think of it as position, orientation, velocity, angular rate, and control inputs applied to the helicopter at each time. We'll work in discrete time. We have demonstrations. And these are noisy versions of what we're trying to recover in these hidden states. We don't know how they're lined up because the pilot executes trajectories at different speeds. But to start out, we'll just do something and initialize that top trajectory. If you have 6 demonstrations, a natural choice is the one of the medium duration you'll put in the top hidden sequence. Once we have that, we can run an algorithm from the speech recognition literature, the Needleman-Wunsch algorithm in biology, dynamic time warping in speech, which will align pairs of trajectories over time. Once you have these alignments, now what you can do is you can run an extended Kalman filter, which will, from the observations, infer the most likely intent of the pilot. So we don't know what's up there. We run now the extended Kalman filter, get out the intent of the pilot, presumably for this particular alignment of demonstrations to hidden trajectory. Now that alignment was starting from somewhat of an arbitrary initialization, so we repeat this process. We go back, erase the alignment, run dynamic time warping again, doing a pairwise alignment between each of these sequences. Once we have the new alignment, we hide the top trajectory again. We rerun an extended Kalman filter, find the top trajectory, and keep repeating this until the process has converged. Let's take a look at the results. So here is again the 6 trajectories that the pilot demonstrated. Now, as a side effect of the procedure I presented, we have them time warped, so now they're all nicely in sync. And the white trajectory here, the white helicopter, is what we infer as the intent of the pilot, what the pilot was trying to fly but never succeeded at flying because it's difficult to fly these helicopters accurately. If you look at this, you could say, well, this looks like a cleaner version than any of the original ones, so that seems the right thing to fly. And that's what we're going to do. But let's take a look at this first a little more quantitatively. Here is a double loop demonstration. 3 demonstrations. After running the algorithm, you get out the black dotted trajectory here, which is a cleaned up version of these color trajectories. So this is the type of performance you get out of this algorithm. Okay, so now we know how to find a good trajectory from multiple demonstrations. The next step is to find a good dynamics model. I'm not going to get into the details of how exactly we did that, but the key idea for the dynamics model is that the dynamics is very complex. If you use just off-the-shelf models that are meant for stationary flight, you stand no chance in these dynamic regimes. So what we did is we said, let's look at these standard models for stationary flight. They have a lot of free parameters. And instead of building one model for the entire flight envelope, for every second into a maneuver, you have its specific model to that point into the maneuver. So we essentially have a sequence of models as you go along this trajectory. Now, each individual model is built in a very similar way to what was done before for stationary flight regimes, but the key insight is that you do need all these different models, one for roughly even every half second along these trajectories. So we get data, built from data, all these models along the trajectory. So let's see how this all fits together. Here is our setup. We have a remotely controlled helicopter. We have a remote control. The helicopter on board has an inertial measurements unit, which carries a 3-axis gyro, a 3-axis accelerometer, and a 3-axis magnetometer. You can think of those as measuring the orientation of the helicopter. There's a radio on board that radios down to a ground computer station what these measurements are at 333 Hertz. There's also a sonar on board which measures distance from the ground in case we do landing maneuvers. And there's also a RPM sensor which measures the speed of the helicopter blades. And to measure the position of the helicopter, we have cameras on the ground. You can also do some of these things with GPS. The problem with GPS, if you fly very aggressive maneuvers, is that your GPS will lose lock of the satellites. So the satellite signal will come in onto your GPS antenna, but your receiver will lose lock if you fly too aggressively, which is exactly what we're wanting to do here. If you go upside down, you also lose lock of your satellites. And you only regain lock after several seconds, which is far too late to stabilize your helicopter. So in practice, we fly with helicopters on the ground for aggressive maneuvering. So these cameras look at the helicopter. They can triangulate where the helicopter is. The vision aspect here is not too hard, actually. You are looking at a helicopter against a blue or cloudy sky, which is not too hard to detect. Calibration setup, you could do some calibration to ensure that you know how you back out position of the helicopter. The position of the helicopter from the cameras gets fed into a computer, so does the inertial measurement unit's data. That gets fused in an extended Kalman filter, which is just kind of, in some sense, the right way to fuse all that information to get out the state of the helicopter. We get out state of the helicopter at 100 Hertz. Then we run model predictive control, which is what I described earlier, where you replan every 2 seconds, every 1/20th of a second, you replan for a 2-second horizon what the right sequence of controls is, and you just execute the first 1/20th of a second of that sequence of controls, and then repeat this procedure. So very frequent replanning. Then the computer goes in the back of the remote control, and the remote control sends out the signal to the helicopter. In terms of experimental procedure, we go out, we collect some frequency sweeps and maybe some step responses from our pilots flying the helicopter, which gives us a baseline dynamics model. Then our expert pilot will demonstrate the air show or whatever maneuver we care about. We learn the target trajectory, as we've seen. We learn a dynamics model from the data we collected. Then we compute the optimal control policy once offline before we start flying. So we find the optimal sequence of controls offline. This helps us while we are flying because when we're replanning, if we have a good initialization, we know ahead of time roughly what the solution will be, we can solve much more quickly. Then we autonomously fly the air show. This will typically succeed maybe 10, 20 seconds into the maneuver, and then it'll start veering off. At that point, our pilot will take control back and put it back into the starting state, and we start again. But before we start again, we take that 10, 20 seconds of data and use that to update the model the computer has for the helicopter. And next time the computer tries, it'll go 20 to 30 seconds into the maneuver. And this will keep growing, and after 10, 15 autonomous trials that are longer, longer, and longer, it'll have built up a good enough model for the helicopter to do the entire thing autonomously. So overall, this will take about an hour, often less, to learn to fly a new maneuver. Let's take a look at the results here. So what we have here is fully autonomous flight, takeoff, flipping over, then hover. What you're about to see now are the maneuvers people have done before, just to check those off. Hover was done before. Forward flight was done before. And then Eric Ferrand's group did the split S, did the snap roll, and did a stall turn, which is a way of changing direction without burning your energy to friction. And from here on, everything are maneuvers that nobody had ever done before autonomously with a helicopter. So a loop with a pirouette at the top. Another stall turn, but coming out tail first. Hurricane, which is a fast backward flying circle. We fly this helicopter up to 45 miles an hour. These are not very large helicopters. Upside down hover, knife edge fall, and then here are some of the hardest maneuvers. Why? Because you're working in the airflow that you just generated, which makes it much harder to anticipate what's going to happen. Here are the flips, much better than in the original video. Tick-tock. And then we end in inverted autonomous hover in this one here. We've also done some other maneuvers like chaos, where you pirouette and flip at the same time, or auto rotation landings, where you switch off the engine and still land safely. So what you've seen so far is a system that can learn from a pilot flying. Any maneuver the pilot could do, our system could learn to fly. So the limit of the system is the limits of what the pilot can do, and it can actually go beyond what the pilot can do because it's a computer. And a computer can be more accurate and more repeatable than human pilots. So I gave this presentation about 4 years ago at the University of Washington. And in the audience there was now a colleague of mine, Blake Hannaford, and he works in robotic surgery. And he said, well, that's all good, flying these helicopter maneuvers. We know that's hard, but how about doing surgery? Right? He said, well, your surgeon sitting on the left here at the console is your pilot. Then the Da Vinci robot parts that go inside the patient, well, and combined with the patient, maybe that's your helicopter. It's kind of the same system. They're always doing surgeries. Just record them, learn from them, and then it should run autonomously. Okay, started thinking about that. One of the most frequently reoccurring tasks in surgery is to do suturing and tie knots. And this is how they tie knots typically with these types of robots. By the way, one thing I should say is, even though this is robotic surgery, and this is done about 300,000 times per year in the United States, these surgeries are all fully done by the surgeon, in that the surgeon makes every motion that needs to be made at the console on the left, and then the robot inside the patient is mimicking exactly the motions the surgeon was making. So it's a way to give the surgeon more dexterity inside the patient while only having small incisions and hence much faster recovery times for the patients. There's a lot of benefit to these types of procedures, but it's still fully done by the surgeon. There's no autonomy built into these systems. So one of the most frequently recurring tasks is tying knots. That's how they do it. They have suture, wrap it around one instrument, and pick up the other end with that instrument and pull through. So we said, let's learn the motions for suturing. People were telling us these motions are somewhat open loop. You don't have to actually model the suture. You just have to go through a sequence of motions that's the right sequence of motion that you'll succeed. We said, well, we know how to do that. We'll tele up our Berkeley surgical robots to do the motions for knot tying, and then we'll denoise them, get out a cleaner version, and execute that and see if we can tie knots. And so we executed the exact same algorithm we had for the helicopter, 5 demonstrations of knot ties. And then here's an autonomous execution. So that's the pickup on one side, wrap around the other instrument. Pick up on the other side.
Holy fuck! First knot tie of the night.
Wow.
Okay, that's student enthusiasm about the success of this knot tie. They said, holy fuck, first knot tie of the night. What that should tell you is that this thing wasn't particularly the most reliable knot tying system out there, and they were super excited they got this to work. It succeeded about 50% of the time. It's not bad, but it's not the kind of thing you want to go into surgery with, or most of us won't want to go into surgery with this kind of conditions. That's one knot tie, right? So what was the problem here? It was very sensitive to the initial conditions. And really what was going on is that really you can't do these things in open loop. You need to close the loop here, and you need to somehow adapt to what's happening to the suture to tie these knots reliably. And frankly, at that time, we were kind of stuck. We said, well, this procedure doesn't work. Let's think about how to solve this. And we thought about it for quite a few years until about a year ago, we came up with a way to deal with this problem. And here's the idea we came up with. What we really want here is very different from what we wanted for the helicopter. For the helicopter, what you wanted is, I want to execute something as precisely as possible. Even when there are some pretty bad wind gusts out there, I want to stay on track. For knot tying, you want to be able to adapt to the new situation, not by renormalizing it into the old situation, but by doing the right new thing for this new situation. So pictorially, you'd have some rope laid out, as in the top drawing. The human ties a knot, and then the robot gets the rope laid out differently, as shown at the bottom, and you want the robot to directly start from there, not first put it in the old format and then tie the knot. So let's take a look at how we're going about this right now, and as I said, this took a while to kind of wrap our heads around how to make something like this work, but now that we know how to do it, it's actually not too hard to explain. Pictorially, let's say you have 4 dots, and the human says, here is a trajectory. So no rope involved here, just drawing a trajectory, a curve. Now you're given 4 new dots, and you're asked to, in this new situation, draw the curve. How are you going to draw that curve? Well, many of us can, in their heads, see what they would do. You would somehow draw a curve that looks similar to the one on top, but a computer doesn't know what that means for it to be similar to the one on top, especially relative to how the dots have moved, right? So what we said is, let's think about this problem as a machine learning problem. And the way we're going to think of it as a machine learning problem is to look at it as follows. You have 4 dots on the left, and both in train and test, and let's assume we know how to register them to each other. If you know how to do that, you can think of these 4 points as samples of a function. So what we have here is samples of a function that maps from R2 to R2. Just 4 examples. It's a lot like something like linear regression. You're trying to recover a line from just a couple of points and fit the best line to that set of points. Here what we're going to do to this 4 points being mapped, we're going to find the best morphing from the first space to the second space that is correct on those 4 points, but is also meaningful in the entire space. And so you can imagine representing the space with this grid to see what happens to this kind of how the space is shaped. And after maybe generalizing to the entire space, this is what you get. I haven't said yet how we get that morphing, but you can imagine that's something you'd want as the result of your procedure. If you know how to do that, then you're in business to generalize that trajectory, because now you can say, well, all I need to do is pick every point on that demonstrated trajectory and apply the morphing to it. If you do that, this is what you get. So what we see here is that if we can somehow register the old situation onto the new situation, generalize that registration to the entire space, then we can map over the trajectory. This was just a trajectory that was drawn, but you can imagine that's the trajectory of your gripper. It could be the position and orientation of your gripper that are being mapped over from the old situation to the new situation. And that way you know what your gripper should be doing in the new situation. How do we find that mapping? So here's the idea. We have a set of training points and test points, and we want our function to map train points onto test points. So that's the constraints in the second line. Now there are many functions that will do that, because it doesn't tell you anything about what should happen for the points that are not your train points. We say we want to find that function among all functions that are available to us, which is a lot of functions, that minimizes the Frobenius norm of the second derivatives tensor. So you take all second derivatives of that function that in the robotic case will go from R3 to R3. It's a bunch of second derivatives, square them, sum the squares of these second derivatives together, integrate over the entire space. That's your number that scores the quality of your function. The best one is the one that achieves the lowest score while getting the training points mapped correctly onto the test points. A lot of options there. One thing I want to observe here first is that the reason we like this objective as a way to determine which one we're going to pick is because this will keep translations and rotations free. So if you could just translate and rotate the old scene onto the new scene, that's free. You're going to pick that. That's good, because often if that's all you need to do, then that's a great transformation to pick. It turns out you can actually solve this very efficiently by just doing some matrix manipulation of the size of the number of examples. So you're not doing a search over all possible functions. You're solving a pretty small problem. This is not something we derived. This was derived by others much earlier. This is something called thin plate splines. And what they showed is that that type of problem has a solution of the form shown there. F of x is some weighted sum of kernel functions. And these kernel functions, kxi, x, xi is a training point, x is where you're evaluating your function. These kernel functions are of a known format shown at the bottom there. So what you really get here is that even though you're looking for the best function among all functions, you know ahead of time that it's going to be a weighted combination of some set of predefined functions. And all you need to find is the set of coefficients here, which is a low-dimensional problem to solve. So we can solve this problem optimally. And let's see what happens if we do this for something like knot tying. So here's the student demonstrating how a knot tie should be done from this situation here for an overhand knot. That's the demonstration. Now, here's the test situation. In the top left, you can see how it is different from the training situation. The shape of the rope is different. You also see in the top left corner, every time it replans, so it takes a snapshot again, it'll register to the train situation at that time. You see how the space gets warped to map train onto test. And then, accordingly, the gripper trajectory gets warped. It gets executed for a couple of seconds, after which it then again takes a snapshot, replans. Here's a different knot. This one here, we didn't see the demonstration, but it's a similar setup where the student demonstrates, and we change the layout of the rope and get the robot to do it on its own. Whenever it brings the arms back is when it takes a snapshot and registers the current situation to the original train situation and replans. So this is all done without any specific programming tailored to tying knots. This is a general approach. We've used this for other tasks that are kind of more standard household tasks. Let's say you want to pick up a cup and pour something into another cup and so forth. Now, for those other tasks, the reason this is interesting is because you can more quickly teach a robot to do the tasks. By default, maybe it takes somebody a day or a couple of days to program a robot to do something like pouring something from one cup into another and so forth. This way, you just do a couple of demonstrations, the robot can learn it. For knot tying, what's really interesting is that to get a knot tied to work takes a real long time, and very few people have successfully programmed a robot to tie knots. And when they've done so, it's often been applicable to just their particular robot or the type of knot they've been looking at. What I want to do in the little bit of remaining time is look at two other robotic settings that we've looked at, not in the same amount of detail, but just to give you a feel of other things that are possible on the motion planning control side. What are we looking at here? This is a four-legged robot, and the challenge here is to autonomously get the robot to go across rocky terrains like the one shown there. Now, the key thing here is that the robot, when you program the robot, you don't know ahead of time exactly what the terrain is going to be. So you have to program the robot to be able to traverse terrains it has not seen before. Now, when it arrives at that terrain, of course, in this type of experience that we're doing here, you get a laser scan of the terrain. So the robot knows what the terrain is, but as a programmer, you don't know what the terrain is going to be. And the challenge then becomes one of deciding cleverly where the robot should place its feet. At least at the time we started working on this, the challenge of making the robot's feet move into the right spots was a solved problem, but choosing the right spots was the hard thing. What is the right spot to place the feet? What's problematic here is that if you put them in the wrong spot, the feet will slip and slide, and then the robot might get stuck, tumble over, and so forth. So what are good spots? We said, well, what matters is you don't want to be on a very steep slope. So steepness of the surface underneath each of the robot feet is important. Another thing that matters is you don't want to be close to steep drop-offs, because if you are, then if you slip a little bit, you'll get a very sudden drop-off for the feet. You also want the center of gravity of the robot to be nicely inside the triangle of the 3 feet that are on the ground. That way it wouldn't fall over. And you might want that with some margin, not just within the triangle, but with margin inside that triangle. So there are a couple of things you care about here. You might care about this at different scales. How steep is the slope, not just at the centimeter scale, but maybe also at the 5 centimeter scale and so forth. So in total, we came up with 25 features that we care about for the robot when it's in a particular stance. Now, when you program a robot to get across in these general ways, what you do is you write an algorithm that plans a sequence of footsteps, and it plans them optimally with respect to some cost function that you define or some reward function. And so what we just came up with here is 25 things that matter to the reward function, but we don't know yet how much each one of them matters. Is it more important to have a margin of 5 centimeters for the CG inside the support triangle versus being more than 2 centimeters from a steep drop-off versus having less than a 5 centimeter height differential between the front and back feet and so forth? It's very hard to come up with the right trade-off between all of these. We tried, actually, and weren't particularly successful. So we said, let's go back to what we also did for the helicopter, which is we took human demonstrations, assumed that that was the right thing to do, and then learn from that what the right thing is to do for new situations. So here, what that would mean is you guide the robot across what is a training terrain, not what the robot's going to have to do on its own in the future, but a training terrain where you demonstrate. In practice, what that means here, you click on a computer screen on foot placement targets, and the robot will execute them one by one, and you kind of guide it along. Then you run apprenticeship learning, which will recover a weight vector that tells you how you should trade off these 25 different features. You say there is a reward, we don't know what it is, it's a weighted sum of 25 features. What the human just did is the optimal thing, is the thing that will optimize the reward function. And we're going to find the reward function that, if the computer were then to optimize that reward function, you get back out exactly what the human did. So that's the idea here, is you try to recover the objective criterion that's being optimized. Then you get a testing terrain. On the testing terrain, you can now compute for every robot pose what the reward function would be. And you can then compute the optimal plan according to that reward function that you learned and apply it to that new testing terrain. All right, so let's take a look at what happens if we set all the weights equal to 0. That means you have no preference between different placements of the feet. And here's what you get. So the low-level controller is trying to do equal spacing foot placements. So it did OK, but it got stuck because it slipped and slid, and that's it. Now here what happens if we learn the reward function, and we choose foot placements optimally with respect to the reward function that was learned. The robot feet still slip and slide. That's unavoidable. But whenever they do, nothing bad happens, because they were placed in a good position, and it nicely gets across. OK, the last little story I want to tell you is about how we might get towards a robot doing laundry for us. So let's look at a first example problem here. The robot might be faced with an image of a sock. And to do something interesting with that sock, it should know, is this sock inside out or not? Where is the toe? Where is the ankle? Is it up or down? And then maybe, if you want to wear matched socks, it should find out which one is the one to pair up with it. I won't have time to go into the details about exactly how we start looking at this, but what we did is we looked at very local features to help us find whether a sock is inside out or not. And it's something we use called LBP, local binary patterns, which essentially looks at every pixel. It looks at the 9 neighboring pixels, or 8 neighboring pixels, and it could be higher or lower, which gives you 256 different possibilities. You build a histogram in a region over which one of these 256 possibilities is the one that tends to be present, and use that as a descriptor for that region in the image. We also use something called MR8, which is a more standard kind of correlation with a filter bank. You feed these features into a support vector machine that tries to classify inside of a sock versus outside of a sock, and it actually works remarkably well. You get in the upper 90s% of accuracy just from a couple hundred of training examples. Another thing we do is look at how the sock might be laid out. We use something called hog on the outline of the sock in the image, assuming we have a way to extract foreground and from background, and then learn an SVM to predict which shape corresponds to toe, ankle, heel, and just regular other parts of the sock. Here are some of the results we got out. So we get reasonable predictions of what the layout is of each of these socks. Far from perfect, but reasonably good. And then if we build this into a robotic system, here's what we get. So this robot is tasked to check whether these socks are inside out or not. It doesn't know how to flip a sock using its grippers, so it uses this pole to get them flipped. Not all of them are inside out, so many of them, after inspecting them, it realizes that they're good, but this one was not. Now it's inspected all of them. It has run a matching algorithm to match them up based on both color, texture, and size. Matches up the ones that have there as pairs, and then one is tray is left over. Another problem you might want to look at is how to fold something like towels. This is something we looked at for a while. And what we did here is we said, well, really what we care about is finding the corners. And so we set up some high-resolution cameras to look at the towel as the robot holds the towel. and use structure from motion. So actually set up just one camera, run structure from motion to extract, so optical flow, structure from motion to extract a 3D shape of what you're holding up. And then had an extractor that from the 3D shape would back out where corners might be. Once we found the potential corner, we would do some fitting to it, see if the robot can indeed get there without perturbing the towel, and then if so, we would execute that grasp and take it from there. So here's the robot. The cameras are actually mounted in the belly of the robot. You can't see them. They're between the kind of extensions of the arms that are moving around. You have the camera sitting there. It's looking at this towel, trying to find a corner. This is sped up 200 times, so it takes a lot longer than what you're seeing here. After it's found two neighboring corners, it'll do this little twisty routine at the top to make sure there is no twist left at the top. So it'll just kind of visually detect whether or not that's a straight line. Once it's found two neighboring corners and there's a straight line between them, then it's a fairly straightforward robot programming task to go to the other table and fold it and put it away. The hard part here really was what's happening at the first table. Okay, so we've seen a couple of things here in action. And what I want to do with this last slide is tell you a little bit about what are some of the challenges I see ahead of us if we want to bring robots into our households and do surgeries. First one is learning from demonstrations. We've been looking at that, but there's a lot of limitations still. Right now, you do kinesthetic teaching where you guide the robot around. Ideally, you could just download YouTube videos. You'd have a computer vision algorithm that understands what's happening, extracts the human demonstration from that. Somehow you map it to what the robot could do and get something out that the robot can learn from. Very far from that being possible, but that would be the kind of thing you'd prefer to do over moving the robot's arms around. High degree of freedom motion planning. So a big challenge here is that if you have a robot with a lot of degrees of freedom, let's say a humanoid robot, which might be what you want in a human-like environment, it can be relatively slow to plan the motions of that robot. And we need to make progress there to make that really fast. Once you can have a robot do things over, let's say, the stretch of 10, 20 seconds, which is the capabilities we look at for the top things there, you want to give it a task for the day. You say, do laundry, cook, set the dinner table, and clean up afterwards, right? And you want it to understand how to decompose that into smaller tasks and then yet smaller tasks and so forth. That's hierarchical planning, and there's a lot to be resolved there. Now, one thing you'll run into if you do what I just talked about is one of the first things you'll run into is that you have so far decoupled perception from control. Really what you want is something called belief space planning. And what happens there is rather than planning in the space of robot joint angles, let's say, and object poses, you plan in the space of probability distributions over robot poses and object poses. What happens then is whenever you get a measurement, that probability distribution will change. Whenever you take an action, that probability distribution will change. And so you automatically will get out, if you plan in that space, the idea of, oh, I might need to sense right now. It'll just fall out if you plan in that space. On the perception side, I think some of the biggest challenges are tracking deformable objects. How do we do that in real time? Another one is a simplification, I would say, of what a lot of people in computer vision look at is how do you recognize instances? In fact, Gary Bradsky, who's one of the next speakers, had a challenge a few years ago, instance recognition challenge, really targeting that problem, saying that if a robot has to work in a fixed household, if ahead of time you can let it look at every 1,000 or 2,000 objects, all you need to do is recognize those objects. You don't need to understand that because one chair is a chair that a completely different looking chair is also a chair. No, that's not needed for a robot to do something useful. So maybe we can look at instance recognition rather than understanding categories. And then the last one there is semantic mapping. The idea there is that if you're going to have a robot go around in a building and so forth, what works really well right now is map out a 3D map of the environment, but that map will not tell you whether something is a door, a drawer, a desk, a chair, and so forth. Then the last one that's not listed on the slide here, but that I kind of want to tie back to the top learning from demonstrations is that you saw the rope knot tying. It's a very challenging problem to tie a knot. But at the same time, one thing is easier there compared to some of the other tasks you might want to teach a robot. And what's easier there is the registration part. Registering a rope in one situation to another situation is a matter of understanding how to follow along that rope. For other manipulation tasks, registering some cluttered scene to some new cluttered scene requires a different kind of computer vision and a lot of challenges there in terms of how do you register an old scene onto a new scene so you can apply that approach. That's another big open problem there. Thank you.
Thank you very much, Peter. Amazing, amazing work. We have a few minutes for questions. If you have a question for Peter, please raise your hand. Someone will bring you a microphone. And please wait for the microphone so everyone can hear your question. Any questions? Over here?
I had the question, when you were doing the robotic flying of the helicopter, what compute power did you have to have behind that?
At the time we had, I think it was 2.1 gigahertz machines. And there was a 2.1 gigahertz machine, dual core. Essentially one core was running the Kalman filter, the other core was running the control algorithm. It would compute controls. The Kalman filter would run on one core at 100 hertz updates. Even though the sensor measurements came in at 333 hertz, we updated at 100 hertz. Then we ran the control at 20 hertz. And we looked 2 seconds ahead. At a 1/20th of a second discretization, that meant 40 discrete time steps that we looked ahead. Now, looking 2 seconds ahead is actually not enough to fly a helicopter reliably. So there's a little additional part that you need to do there, which is you want to make sure that at the end of the 2 seconds, you land really where you want to be. You don't just want to optimize equally over those 2 seconds. Where you end is more important than where you are throughout. And so in the offline computation, when we find the optimal sequence of controls offline for the entire maneuver or the entire air show, we also compute a second derivatives matrix of if you were to deviate at a certain point along the trajectory, how much would that cost you in the future to have that amount of deviation? So we have a pre-computation of how bad it is to deviate from the trajectory. And that's what we use at the end of the 2 second horizon. And that's what allows us to just look 2 seconds ahead rather than needing to look a whole maybe 20 seconds ahead to make it work. But 2 seconds look ahead was our limit of what we could do at the time.
Any other questions? If you have a question, keep your hand up. Someone will bring you a mic while the previous question's being answered so we can get maximum throughput.
So in the helicopter application, how big was the Kalman filter?
How big was the Kalman filter helicopter application? We had position, 3 degrees of freedom, orientation, another 3, derivatives of that, so that's another 3 and 3, that's 12. We then had the second derivatives of that, making it 18. We had, so that's 18 for essentially the rigid body. The reason we had the second derivatives was mainly because of the way we modeled the helicopter, because you have a dynamics model in there. The other reason is that we got in accelerometer measurements, which are second derivatives measurements. So we kind of needed somewhere in there to be able to incorporate those measurements. And then there were an additional 3 state variables, or 21 total, that were tracking the bias on the gyros. So the gyros have a temperature-based drift that's not perfectly compensated internally. And so we set the helicopter still when we start out, 0 out the bias, because we know it's not rotating when it's sitting on the ground. But then over time, that'll slowly drift that bias, and so we need to track that too. So 21 degrees of freedom in the Kalman filter.
I think there's another question over here on the right.
So in tying the knots, did you consider the situation where the thread has some stiffness?
Okay, great question. So one of the things that makes surgical knot tying harder than what we did with this rope over here so far is that they have a lot of energy. A lot of energy gets built up if you bend them, right? These surgical sutures. And so you'll often get more motion. For just a little bit of motion at the ends, you'll get your suture to move quite a bit. And it'll also depend on exactly, there's a little bit of kind of twist in it. It might move to the left or the right depending on the exact twist you have. We haven't looked at that yet. I think to do that, what we need to do as an extension of what you saw here is to learn from many demonstrations. So right now what you saw is one demonstration generalizes reasonably well, but what we really need is maybe get a couple hundred demonstrations, then each type of scenario of how things will kind of bend off to the side will likely be covered by those demonstrations, and we'll then be able to map from whatever is the closest match. So I'm optimistic it'll work once we can work with multiple demonstrations and have a good way to pick the right one.